Hello everyone, this is Refeel Riaz from Department of Astronomy, University of Concepcion, Chile, and I'm here to present some of our group's findings related to the stellar initial mass function. The theme of this presentation is about how the fragmentation and the mass accretion processes can affect the stellar IMF. At the bottom, you are watching my group members from left to right. That's me, then Dominic Schleider, followed by Siegfried van der Verbeek, and at the last, Rolf Klessen. We now begin our presentation. Okay, to have a quick background, let's see when and where the first star formation actually occurred in the cosmos. For this, we have to go back in time. Cosmological simulations have given us the idea that just after 400 million years from the Big Bang, first generation of stars called POP3 stars came into existence. And these stars were formed inside the dark matter mini-halos, which themselves were trapping the primordial gas inside them. The primordial gas was having molecular hydrogen as the main cooling agent, but still the cooling was not efficient enough, hence the temperature was quite greater than what we observe in today's star-forming regions. That's why the first generation of stars were quite massive, mainly because the temperature is high, and hence the Jeans mass prevailing in those conditions were quite high. Keep in mind that the Jeans mass is the minimum mass required for any clump of gas to become a self-gravitating object, and hence move forward to become a star. So the first generation of a star was quite massive, and since they were quite massive, they have relatively short time to live. Soon they become supernovae, and when the supernovae occurred, they give birth to new chemical species in the star-forming regions. Among these chemical species, carbon, nitrogen, and oxygen were the key players, providing the metal line cooling, hence making the temperature to drop down for the next generation of a star-forming gas. Along with these chemical species, there was also dust available in this environment. So overall, the temperature for the next generation of a star called the POP2 stars were quite low, and hence we expect from these POP2 stars to be less massive than POP3 stars. And then we proceed further for the next generation of stars called POP1 stars. So the important point is that the temperature at the beginning was quite high, but not later on, just because new chemical species were coming into existence along with the dust, and these were making sure that the temperature of the star-forming regions were dropping down to a level where the Jeans mass becomes quite low. Apart from the species which actually offer the cooling, we must not forget that the CMB radiations was also there to regulate and affect the star-forming environment. At the moment, in the Milky Way galaxy, in the present universe, we see that it's just 2.7 Kelvin. But back in time, when the universe was quite young, we expect that it was not 2.7, it was more than that. Hence, we assume that at the beginning and then later on, the universe, when it was quite young, the CMB was efficient enough to actually regulate these star-forming regions. And there is a concept of a stellar initial mass function, which is actually the ratio of the low mass stars to the high mass stars. In a newborn stellar population, this initial IMF is expected to be universal. But if you see the diagram on the left, you see that we expect from the IMF that for high mass stars, they are low in number. But if you move towards the low mass stars, the number starts increasing, and then the trend starts shifting, which means that this is the IMF we expect. But in the young universe scenario, we expect that this IMF is little different, in a sense that you can't simply say that it is universal. throughout the history of the universe. Back in time, it could be of different nature. So in our case, we are going to address whether the CMB is actually effective enough to regulate the star formation and hence to change the stellar environment, hence changing the IMF. For this, we set up a simulation in which we have a sphere of gas which is equipped with metal line cooling agents. It also has efficient dust cooling available for it, and also the gene's unstable condition is prevailing, which means that the gas sphere is about to collapse. And in the background, we assume that the CMB is actually regulating the temperature of this star-forming gas. To begin with the simulation, we use a particle method called grade SPH, which is the smooth particle hydrodynamics technique. This is a particular code related to the SPH we are using in our simulations. So what we do is we construct, with the help of 0.25 million particles, the sphere of gas of a certain mass. Right now it is 30 solar masses. It has a radius of around 0.16 parsec, and the density at the beginning is 10 to minus 19 grams per centimeter cube. This gas sphere is also in solid body rotation, which is mentioned by the rotational parameter beta, that is 1%, which is actually the ratio of the rotational energy to the gravitational potential energy of the system. It is very important to mention here that when we set up a simulation, we must know that to what scale or to what mass the simulation can give us a correct results. So we are quite sure that whatever star is happening, if it is of 0.01 m0 and greater than this value, we are actually resolving it quite smartly, which means that we are quite okay with the numerical simulations. Whenever the star is formed in the gas, it has to have an accretion radius around which, within which if a material falls in, it becomes the part of the protostar. So for this, we set the accretion radius equals to 1 AU. And whenever the density reaches to 10 to minus 10 grams per centimeter cube, which is with respect to the density with which we began, is 9 orders of magnitude change. Whenever this happens, we form a star inside the collapsing sphere of gas. So these stars were formed only when the density of the gas reaches to 10 to minus 10 grams per centimeter cube. So what we do is we set up a simulation, and we have 5 models, and we run these 5 models with 2 seed values just to have good statistics. We begin with 10 Kelvin core, and then 20, 30, 40, and 50 Kelvin cores. Remember, these temperatures are actually assumed that it is the CMB which is regulating the star-forming regions and giving the star-forming regions these temperatures. And this range of temperature is actually covering the redshift value from 2.7 to 17. Within this span, we expect that the star formation is happening under the influence of CMB, which is regulating the star-forming gas and setting up the temperature of the star-forming gas from 10 Kelvin to 50 Kelvin. It is important to notice that for a colder gas environment, we got more stars coming into existence, and it's more in a filamentary structure. But on the right side, you see that the most warmest of the core is forming a lesser number of protostars. And actually, the filamentary structure is also not very pronounced. However, it is also very important to notice that how we carry on with the thermodynamics of the system. For this, we consider the equation of a state called the barotropic equation of a state. What we do is we try to mimic how the transition from isothermal to adiabatic collapse occurs in these star-forming cores. So whenever the density reaches to a specific value, we expect that the isothermal regime of collapse is taken over by the adiabatic regime of collapse. And when this happens, the gas is starting up to get more heat up, and you expect the evolution to carry on along with this temperature environment. Then we have some statistics. With all these 5 models run with 2 seeds, we got some statistics to analyze how the system is really evolving over the period of time. For instance, we try to analyze how the mean masses are evolving in the systems, and how the maximum masses are responding, the minimum masses are responding, and stuff like that. So we try to analyze all these things, and what we do is we try to analyze it with respect to the star formation efficiency, which is actually the amount of gas converting into stars. So we analyze our upcoming data with respect to the star formation efficiency, which is 2%. Then we analyze the case at 5% star formation efficiency. We let the gas to evolve further, and when the star formation efficiency reaches to 10, we again analyze the system. And then when we reach to a 15% star formation efficiency, we stop our simulations and we try to analyze the entire evolution along with this star formation efficiencies. So what we observe is that with the help of the star formation efficiencies at 2, 5, 10, and 15% values, we analyze the mass spectrum appearing in these star-forming cores. Remember, the color scheme, the blue and the red, the orange, purple, and the green are respectively the 10, 20, 30, 40, 50 Kelvin gas clouds. So when we begin and we reach to 2% star formation efficiency, we see that there is not really a trend available. Regardless of the core, whether it is the warmest core or the coldest core, we see that the masses of the protostars are all over the place. There is no real trend actually there. Then when we reach to the 5% star formation efficiency, we start seeing that there are some trends appearing, in a sense that more massive stars are forming only for the warmest cores, while the less massive protostars are forming more with a case in which the core temperature was relatively low. We move forward to 10% star formation efficiency, and we see that the warmer cores yielding more massive stars. And the trend actually continues when we reach to the 15% star formation efficiency, which is the termination point for our simulations. Here we see a clear picture that all the protostars which are more massive, they belong to a more warmest cores, while the coldest cores are now yielding protostars with lesser masses. Lesser masses are not really available in the warmest of the cores. Okay, in case if you're thinking that why the massive protostars are very few in numbers, because along the y-axis you have the numbers, yeah, while the massive protostars are too small in number due to the Jeans mass. In these cores, the Jeans mass was very high, and it is very difficult for every clump of gas to qualify for the self-gravitating objects. That's why we expect lesser number of protostars. Then we also analyze the mean masses. Here, some interesting trends are available. We see that when we reach to a star formation efficiency around 5, we expect that there is a transition going on from fragmentation-dominated regime to the accretion-dominated regime. What happens is that within the fragmentation-dominated regime, which is the earliest part of the evolution, we see that there is not a real trend available for the mean masses. I mean, it's all over the place. But if you see the top panel, you will see that when you reach to a star formation efficiency around 5 and beyond this, here comes the trend. More massive stars in terms of their mean masses are forming and belonging to the warmest of the cores. The coldest cores are yielding relatively less mean masses, which means that there is a trend. The mean mass is going to be associated with a higher value for warmest of the cores only when you reach to a particular value of a star formation efficiency during the evolution. And that particular value is 5% around. And if we look at the bottom panel, we see that the second seed value, in the second seed value, again, we observe a similar trend, in fact, more pronounced, that once you are in the fragmentation-dominated regime, there's not really a trend available to actually claim that the mean masses are higher for the warmest cores. But once you reach to the accretion-dominated regime, you see that there is a clear trend that the mean masses were quite higher for the warmest cores, and for the coldest cores, they are really small. So this is the trend we observed for the mean masses. Similarly, we also analyze the maximum masses prevailing in these star-forming cores. Again, we see some trend with respect to the transition that is happening between fragmentation-dominated regime to the accretion-dominated regime. And again, we see that there is a clear trend coming up after the 5% star formation efficiency, which is giving us the idea that there is some transition available within these collapsing gas clouds called the fragmentation-dominated regime and the accretion-dominated regime. This transition is very important. We also analyze the number of protostars. Again, we see this, that once the protostars are forming and the regime is fragmentation-dominated, we do not see a real trend. But once you reach to the accretion-dominated regime, you start seeing that there is a trend available, that more stars are forming and less stars are forming for the warmest core and more stars are forming for the coldest cores. Keep in mind that the less number of stars are forming for the warmest cores mainly because the Jeans mass is quite high. Whereas for the coldest cores, the Jeans mass is fairly low, and most of the clumps forming in the cloud, they are actually qualifying to become self-gravitating objects and eventually become protostars. So, but we must not take, we ought to consider that there are certain missing aspects involved in our simulations. For instance, we did not take into account the magnetic field, which can actually slow down the collapse. Maybe it can affect the transitions where it is happening. And also the radiation feedback, once the protostars are forming, they're gonna start affecting the environment as well. So this is not the part of our simulation. So we ought to take into account this particular aspect as well. Then comes the more realistic EOS. Barotropic EOS is fine, but it's a makeshift arrangement. We ought to solve the energy equation. And with this, perhaps we can actually come up with a concrete idea that yes, there is a transition available inside the collapsing gas cores. So my conclusions are, we have got the evidences that the fragmentation and mass accretion regimes are present, and the mean masses and the maximum masses are actually responding to these transitions. And the average masses are actually regulated more by the gas temperatures prevailing in these collapsing gas. A very important part is that the star formation efficiency, around 5 to 7%, is very critical. It actually determines the warmest gas clouds and the mean masses for these collapses. And then also the maximum mass is also responding to these star formation efficiencies of around 5 to 7% value. To cut the story short, the IMF can be affected if we take into account these transitions and if we take into account the CMB radiations affecting the star forming regions. With this, I say, thank you very much for your attention.